friends, colleagues, both here in person and checking in from online and Zoom. My name is Evan Thornberry. I'm the head and curator here at the David Rumsey Map Center, and I am really excited to welcome you all to the 5th Biennial Barry Lawrence Ruderman Conference on Cartography. Tonight marks not just the opening of our multi-day conference, but also this fantastic exhibition that all of the speakers for this conference submitted objects for and has been expertly assembled by our assistant curator, Christina Larson, in the back. Thank you, Christina. It looks fantastic. I'd like to acknowledge that we are gathered here on the traditional and ancestral territory of the Muwekma Ohlone people. And as we engage with topics of history, science, geography throughout this conference, I invite everyone to reflect on Indigenous perspectives and knowledge systems related to our theme and the land we're on today. Above and below, mapping the unseen, the hidden, the misunderstood, the mysterious, from underwater landscapes and intricate cave systems, the networks that make up our information economy, and onto the almost tangible atmosphere and into the universe and beyond. This year's conference will chart the Earth's layers and our place in the wider universe. It's very hard for me to believe that we've been planning this conference for almost 2 years, since December of 2023, shortly after the previous conference. Some of you may have been here, with a conversation between Barry Ruderman, Stace Maples, many of you know, who is the Stanford Geospatial Center manager and was the interim director here at the Map Center for much of 2023. Was a phone call where we decided on the theme, above and below. Mapping anything but the surface of the Earth was how we originally described it. Very cool idea, and it's proven to be a really unique and exciting topic to design a cartographic conference around. This was also the first time we assembled a steering committee to take ownership over the theme and lead the speaker selection process. And I'd like to thank our steering committee members, Stace Maples, Alex Clausen, Jen Frazier, and RJ Andrews, who are not here today, but will be here tomorrow. We all contributed thoughts and ideas to secure this a set of interdisciplinary speakers, integrating science and technology with historical, cultural, and cartographic topics, and ultimately making this conference program such a widely applicable and successful program. I have so many more people to thank. I'm gonna try to be brief. Hosting a multi-day conference like this is a heavy lift for our small but mighty staff here at the Map Center, so many other people have contributed. I'm going to, as I said, I'm going to keep it brief. We'll hold applause to the end. RJ Andrews, who not only did he participate in the steering committee, but designed our fantastic t-shirts. We have a limited number of them. If you can get one in the back, please do. They're awesome. Thank you, RJ. Conference volunteers, you'll find at the registration desk in the back and also in the elevator corridor behind me. Mostly Stanford Library staff and Stanford students. Zoe Dillis, Mimi Tartar, Emily Ducarneau, Alejandra Ricon, Satya Vargas, Alma Gallagher, Jesse Kong, Lamona Niu, and Mariam Tsenge. Thank you very much. Laura Kruger, our assistant, or our cartographic metadata librarian. I don't know if there's Laura back there. Laura, thank you. Your ability to step up and help wherever you can, whenever needed, does not go unseen. Thank you so much. Among one of the many other things that Laura did this conference was select a number of things that are going to be in our tour on Friday morning of special collections. So thank you for jumpstarting that tour and the planning around it. Niles Dorn, who is, he's worked with all of our speakers so far to get them set up for their presentations. And while Niles has many roles here at the center, he is our go-to AV support person. And thank you in advance, Niles, for all the help you're going to provide tonight and over the next couple of days. And I'd like to thank our speakers who we're all eagerly waiting to hear from over tonight and the next couple of days. You have responded to countless emails from me and other conference organizers. Thank you so much. You have all been lovely to work with. Let's give everyone a round of applause, please. But wait, there's more. Christina Larson, I mentioned our assistant curator, worked with each of the speakers to curate this exhibition. This is a monumental task coordinating, delegating, and timing everything involved in this installation. She overcame this even after being summoned for jury duty in the weeks leading up to this conference, so thank you, Christina. Martha Martinez, executive assistant in our university librarian's office, and Laura Swenson, our operations manager here at the Map Center. I know Martha, I see Martha in the back. I don't know if Laura's out right now. I cannot express enough gratitude for all of the work each of you did to make this conference happen. Without you, we would not be here. We wouldn't be able to organize the logistics around this. We have been meeting weekly since May, the three of us, and so much has been accomplished over that time. I feel like we're in amazing shape tonight for the rest of this conference because of you. Thank you. And of course, Barry Ruderman of Barry Ruderman Antique Maps, and Alex Clausen, business partner at Barry Ruderman Antiques Maps, and of this conference's fame, of course. None of us would be here without you. Thank you for your ongoing support and generosity. You've made it possible, once again, to bring a room full of map heads together for another cartographic conference, and we are truly appreciative. Thank you. So before I hand the mic over to David Rumsey for his remarks and introduction of our speaker, I have a couple of announcements and housekeeping items for you. First and foremost, everyone who's registered for the conference, for the in-person conference, has a name tag. Please wear it. This will help all our colleagues down at the entrances immensely. So if you could, it'll help just alleviate any friction when entering the building. We've pre-registered you as guests here. There's one gender-neutral bathroom on this floor. The key is available on the front desk near the pillar. There are other restrooms on the third and second floor of this building. If you would like directions, just ask one of us. We have coffee breaks scheduled tomorrow and on Friday, which are upstairs in the beautiful Bender Room. We'll show you the direction how to get there. Please help yourself to coffee and refreshments, but do not bring food or beverages back to the David Rumsey Map Center. We're watching you. We have a strict no food or drink policy in the space. On Friday, our field trip to view material and tour our special collections unit has limited capacity. If you would like to join us, please submit your name to the sign-up sheets in the back. There are two groups. We're asking for your name and your phone number. If you are not planning to make it, please don't sign up. We think we're gonna fill up. So let's reserve space for those who are committed to coming. And finally, all of the talks you see as part of this conference will eventually be made available in our YouTube channel. We will announce this in our newsletter when they're available. And if you'd like to subscribe, there are QR codes on the registration desk. And for those of you in Zoom, you can find our newsletter registration link on our website. So I'm looking forward to enjoying and being part of this conference with all of you. Thank you for being here, and please join me in welcoming David Rumsey.
Thank you, Evan. Welcome, everybody. It's wonderful to be back here. It's hard to believe this is the 5th Ruderman conference. I was saying to Barry, 9 years pass pretty quickly. We began in 2017 with a general conference on young cartographic historians, and we also debuted the Urbano Monti map that year, which Barry had found for us. So forever grateful to that. And then we had in 2019 quite an interesting one on gender and sexuality and mapping. Not your normal map conference topic, but it was very lively and interesting. In 2021, we had indigenous mapping, which was fantastic. A lot of new information for a lot of us coming out of that one. And then the last one, 2023, data visualization, one of my favorite subjects, and that proved amazing. This year, mapping above and below is, you're gonna see the range of talks is literally that far from way up high to way down below. It's a mix of science and cartographic history, visualization, just a wonderful group of things over the next 3 days. I'll just give a little brief summary of what we're going to be in for. So our 11 speakers will trace how humans have mapped the visible and invisible worlds, from the ocean floor to outer space, and how these maps have transformed our understanding of the Earth and beyond. We'll begin today with Marie Tharp's revolutionary seabed maps, some of my favorite as a collector, which redrew the planet's hidden topography and helped establish, interestingly enough, the theory of plate tectonics. Then we're going to turn tomorrow to the ambitions and uncertainties of early modern weather makers who sought to chart and control the atmosphere itself. From there, the talks will descend into the subsurface, where radar imaging now allows scientists to visualize structures and dynamics between ice sheets and the frozen crusts of distant moons. Then further on, we're going to broaden outward to the visualization of clouds and oceans and global energy flows from satellites, and then far beyond into the Sloan Digital Sky Survey's vast mapping of galaxies, stars, black holes across cosmic time. Alongside these scientific frontiers, the human and artistic dimensions of cartography will emerge in the craft of modern globe making, where stories of identity and memory are inscribed into spheres, and then in the long history of oceanographic exploration and the evolving technologies of seafloor mapping. And then also the invention of new imaging systems from NASA that extend our capacity amazingly to see through water and atmosphere and planetary surfaces. We'll also look backwards to the early cartographers of caves and subterranean spaces, whose maps navigated the border between faith, conjecture, and evidence. And finally, we'll come forward into the digital age, when maps of the internet's undersea cables and data networks reveal another kind of hidden geography, the physical infrastructure that underpins our virtual world. So taken together, these talks, they move fluidly between scales and centuries, linking art, science, and technology, which we always expect from maps, to ask how the act of mapping, whether of deep oceans, icebound worlds, or stormy skies, global networks, continues to shape what we see and what we know, and how we imagine our place on this planet and in the universe. It's really going to be an extraordinary program. I'm very excited about it, and you'll see on the walls, all of the speakers have chosen images to represent their talks. So to start off our program today, we're going to hear from Betsy Mason, whose keynote talk is Illuminating the Deep, How Marie Tharp's Pioneering Maps Revealed the Ocean Floor. Betsy Mason is a freelance science journalist and editor based in the San Francisco Bay Area. Her work has appeared in numerous publications, including National Geographic, the New York Times, Nature, Scientific American. She's co-author with Greg Miller of All Over the Map, one of my all-time favorite map books, which is an illustrated book of stories about maps and cartography for the National Geographic. Betsy was senior editor at Wired magazine, in charge of online science coverage from 2008 to 15, and from 2015 to 16, she was a Knight Science Journalism Fellow at MIT. She's got a master's degree in geology from Stanford and is a graduate of the UC Santa Cruz Science Communication Program. She also serves as secretary of the board of the Council for the Advancement of Science Writing. So please welcome my dear friend, Betsy Mason.
All right, looks good. I hope you're not disappointed that I'm not talking about that US soils map that was up there for a second. It's really, really pretty as well. I am really honored to be here. particularly because I am not a cartographer or a historian. I'm just a map-obsessed journalist. Let's see if we can get this out of the way of my notes here. And a former geologist. I'm also a huge fan of David Rumsey, who invited me into his home to see his collection in 2013, which was a really big deal for me back when I was first starting to write about maps. One of the most fun afternoons I've ever spent. And I'm grateful to Barry Ruderman for organizing this conference every 2 years. It's fantastic. And it's always fun to be back at Stanford, where I got my degree in geology, we'll just say some years ago, and actually where I was born some additional years ago. So I have always loved maps, but my obsession with them didn't start until I started writing about them. And the more I learned, the more I loved them. I also found that they are a great way into stories for a journalist. Oh, hi, Elizabeth. I didn't see you there. I started a blog about maps at Wired when I was science editor there with Greg Miller, my co-author on the book as well, and we eventually moved it to National Geographic and then turned it into a book in 2018 for National Geographic. And so when we were first thinking about making this book, we both had a handful of maps that we were just not willing to have a book without them in it. And this map that I'm going to talk to you about today was at the top of that list for me. It is the crowning achievement of geologist and cartographer Marie Tharp, and it's the only 2-page spread in the whole book. So in this talk, I'm going to try to do 3 things, at least 3 things, probably too many things. I'm going to show you how the map was made. I'm going to explain the impact it had. Spoiler alert from David, plate tectonics. And I'm going to argue that Marie was the only possible person who could have made this map. And I'm also hopefully going to convince you that this is the most beautiful, impressive map of the ocean ever made, and probably that ever will be made. Okay, let's get started. So here is that same section from the title slide. I think it's gorgeous. The colors, the relief, the detail, it's amazing. But it's also a really impressive scientific accomplishment. So the focal point of the map and this section of the map is this mid-Atlantic ridge, this subsea mountain range. And it's also that is also the center of the story of the scientific importance of this map. So this ridge is an enormous structure that runs through the center of the Atlantic and most of the oceans on Earth. But despite being so big, because it is hidden underneath an entire ocean, it was basically unknown until the second half of the 19th century. At that point, economic and scientific interests inspired people to try to figure out what was down there. So I'm going to go through a very abbreviated history of ocean floor mapping, since you'll probably get a better view of this from fellow journalist Laura Trethewey on Friday. This map from 1857 is the first time that you get a little hint of that mid-Atlantic rise. This was a map made by Matthew Fontaine-Maury. He's known as the father of oceanography. We have a story about him in the book. And he called this rise the Dolphin Rise. The data is really sparse, as you can see, so he had to correctly inferred a continuous ridge there. So this quote appears at the beginning of the paper that accompanied the publication of Marie's first map. Fontaine-Maury says, "Could the waters of the Atlantic be drawn off, the very ribs of the solid earth, with the foundations of the sea, would be brought to light, and we should have presented to us at one view the empty cradle of the ocean." There's a much longer quote, and it's all beautiful like that. But in essence, this is what Tharp would do a century later. This 1877 map is from the Challenger expedition, considered the first major ocean science voyage. And part of the motivation for the expedition was to create better maps of the ocean floor for the benefit of planning where to put subsea telegraph cables. And the depths were measured by sending a 200-pound lead weight attached to a rope to the bottom and measuring how far down it went. But here you can clearly see that continuous rise. At the turn of the century, Prince Albert of Monaco funded an effort to collect all of the best data onto one ocean chart. This project is still ongoing. It's now known as the General Bathymetric Chart of the Oceans, or GEBCO. And this is from the first set of maps published in 1903. This one was first published in 1912 in the second edition, and the third edition that was published in the 1930s did not update almost any of the Atlantic Ocean. So the data is still pre-1912. The ridge is starting to come into view, but it's still pretty diffuse. And at the time when Marie got started in the late 40s, early 50s, the public conception of the ocean floor was just basically a flat, featureless bathtub bottom. But Marie's work would change that. All right, so let's meet this woman. I kind of love this picture of her. And the fact that she was a woman is important, not because she broke barriers and ceilings and laid foundations and paved pathways and all that. She did all that. But I would argue these maps could only have been made by a woman at this time. So her gender meant that certain professional avenues were basically off limits for her. But she was able to take advantage of doors cracked open by various historical circumstances and became uniquely qualified to make the significant contributions to both science and cartography that she did. So without her, the maps would not exist, is my argument. Marie's father worked for the USDA's Bureau of Chemistry and Soils, making soils maps, and this is her in the early 1930s with his tripod. She's quoted as saying, "I guess I had map making in my blood, though I hadn't planned to follow in my father's footsteps." But this may have been partly because that wasn't really an option for women at the time. So in the 1940s, higher educational options for young women were pretty limited, particularly in the sciences. And Tharp was a student at The Ohio University in 1941. She was studying music and English and switching majors every semester, as she put it, casting about for what to do with her life when Pearl Harbor was attacked. So suddenly all the young men were leaving the campuses and heading off to war, and there were a lot of empty seats. So the University of Michigan Geology Department decided to deal with that by allowing women to join the department for the first time. So Marie was among the first group of 10 or 12 women to enter geology graduate school there in 1943. When she graduated, she took a job with an oil company in Tulsa, but the women there were basically doing super boring microscope work, in her opinion. And so she started taking classes at the University of Tulsa and earned a second BS degree in math. And in 1948, she took all her degrees and went to New York City looking for a challenge. Those degrees did get her an interview in the Columbia University Geology Department, but still the only position they would hire her for was of research assistant and draftsperson to male graduate students who had not yet earned the degree that she already had. But she took the job anyway, and this ended up being a huge opportunity for Marie. A few weeks after she started, Bruce Hazen arrived, fresh out of college. This is obviously not a picture of him fresh out of college, but good pictures of him are hard to find, and I like this one. He looks very nice. So soon Marie was working exclusively as Bruce's assistant, and she worked with him through his master's, his PhD, and his entire career as a geologist. Marie and Bruce were among the first scientists to work here at this estate in Palisades, New York, that was donated to Columbia by the Lamont family. It became known as the Lamont Geological Observatory. And there was a big focus on the ocean there. The director was a geologist named Maurice Ewing, also known as Doc. So one of the first things Marie did at Lamont was mount the 16 sheets of that third edition of the ocean floor chart on the wall outside the office where she worked. So the data at this point is more than 35 years old, but this is still the best available map at the time. So echo sounding to get depths of the ocean floor was invented in the 1920s. They measured depths by sending pulses of sound down and basically using a stopwatch to measure how long it would take for the sound to bounce off the ocean floor and return to the ship. But this method was not really extensively used until after World War II. This ship is the RV Atlantis. It was built in 1931 for the Woods Hole Oceanographic Institution, and this is the first American ship built specifically for this purpose. It collected hundreds of thousands of miles of ocean depth data by the time it was done, and provided a good chunk of the data that Marie used to map the ocean floor. And fun fact, the space shuttle Atlantis is named after this ship. More ships. In 1953, Lamont bought this research vessel. I don't know, I'm gonna call it Vima. I don't know if that's actually how you pronounce it, but they outfitted it with the highest tech at the time, a new echo sounder known as a precision depth recorder, which had a much more focused sonar beam and a very low error of less than 1% of the depth of the ocean that it was sounding through. So Bruce spent most of his time on this ship collecting data, and had things been different, or had Marie been a man, she probably would have been on that ship too. But women were not allowed on the ships, even women with advanced degrees like Marie. So she was primarily analyzing the data and creating topographic profiles along the ship tracks, and then creating the maps. So here are the ship tracks that they used from those two ships to make their first map of the North Atlantic. So the first step was to take all the depth soundings from these tracks and convert them into depth profiles, basically vertical slices through the crust. And this is what this looks like. This data is a little bit older than what they were using, and it's from the South Atlantic, but it gives you a good idea of what that looks like. These are very vertically exaggerated in order to show the topography, which was typical when you're trying to interpret the topography. So previous ocean maps had then used the depths to create a contour map of the topography known as bathymetry in the ocean by connecting dots of equal elevation. So this gives you a little bit of an idea of how you might do that. And there's some interpretation involved trying to figure out where the valleys and the ridges go. But the result is a bit abstract, and you do have to have a little bit of knowledge of maps in order to be able to read what's going on there. So Marie and Bruce opted for a different technique known as the physiographic diagram. So this involves making sort of three-dimensional sketches to represent the terrain at an oblique angle so that they kind of look like how a view from an ocean, from a plane window would be. This was possible because of Marie's training. Most of the assistants and draftspeople did not have degrees in geology or much training in science at all. They really didn't need it they were basically just plotting thousands of data points, very rote. But because she had studied geology, she had a really good understanding of landforms, and she was able to use that to look at these profiles and make her best guess at what those structures might be. And she thought of as the quote there, she thought of the little bit of information that you get under the ship tracks as ribbons of light. And the next step was to visualize what was in the darkness on either side of these ribbons of light. So by looking at two parallel profiles, she would try to match up the highs and lows and then interpret what would be connecting them in between. I think you can think of this as an act of informed imagination. This method is not usually meant to show each peak or seamount, but to give an impression of the topography, which made it ideal for a landscape that nobody could actually see. So the result looks something like this. It's an attempt at a realistic impression of the seafloor. As Marie put it, there is only one proper way to sketch or to contour the ocean floor, and that is to present it as it actually exists, as it would be seen if all the water were drained away. So in this work, Marie was greatly influenced by the man who invented this technique, Armin Lobeck. She studied his block diagrams textbook in college. This is just one of the many figures that I chose to pull out that gives you some idea of how he tried to systematize the illustrations. This is his 1948 physiographic diagram from David's collection. His first US map was published in 1921. Here's a little bit of a close-up of where we are, and you can see there's still a little bit of fuzzy caterpillar action on there, but you can get a sense of the 3D effect. So the map nerds among us may be familiar with one of Lobeck's other disciples. Anybody recognize this guy? Yeah? That's right. And pronounced his name correctly. He's one of my favorites, Erwin Royce. There, you can see it. Spelled Royce. I did learn that pronunciation from one of his sons, so I'm pretty sure it's right. This map from 1957 of the US is one of my favorites. I love the way that it gives you an impression of what's actually there. You don't need to understand how to read a map to understand the information here. As Royce put it, the map appeals immediately to the average man. It suggests actual country and enables him to see the land instead of needing an abstract location, instead of reading an abstract location diagram. It works on the imagination. And so this is one of the reasons the method appealed to Bruce and Marie. It was accessible and evocative of the actual terrain, and it was perfect for a landscape that you couldn't actually see. But they had another reason for using this method. We're in the Cold War era, and the US Navy had decided to classify precise depth locations once they were able to gather them with that precision depth recorder. Because that information could be used to figure out where submarines could go without being detected, where they could hide, where the dangerous seamounts were, and they did not want to provide this information to the enemies. But using the physiographic method sort of displaces the actual location of those depths enough because of the sketching and the 3D effect that they were allowed to publish the map. And this is what that looked like. And this is one of the maps that we've got on the wall over there. This one was first published in 1957. At the time, Bruce was doing some work for Bell Labs related to subsea telegraph cables, and so the first publication was a Bell Labs technical paper with Bruce and a Bell scientist as the authors. This identical version was published in 1959 by the Geological Society of America with Marie as the second author. And a couple things I really like about this map are you can see the Cape Verde Islands breaking through the neat line down at the bottom, and then also the mid-ocean ridge breaking through at the top. Marie said of the legend, like the cartographers of old, we put a large legend in the space where we had no data. I also wanted to include mermaids and shipwrecks, but Bruce would have none of it. Here's a little close-up. So Bruce was not completely uninvolved in illustrating the terrain. Apparently, they argued quite a bit over specific seamounts and what went where. And sometimes he would follow behind her and erase her work, and she would have to come back and redo it again. This is a clearly posed photo taken by National Geographic much later, but I like that it shows Marie actually making the map and Bruce in the background sort of offering some data, and she doesn't seem to even really notice he's there. So cartographically, this map is groundbreaking. It's the first time that this method was used to characterize an unseeable landscape. Historically, it's just a major leap forward in the detail of ocean mapping that we had at the time. But it also had a huge scientific importance. Understanding that importance requires a little bit of knowledge of plate tectonics. I'm sorry. Anybody? Well, I know there's at least one person who understands plate tectonics here. Oh, hi, too. So in 1912, Alfred Wegener proposed the theory of continental drift. So you've probably heard of this theory. He thought that the continents used to all be joined together in a supercontinent called Pangaea, and for some reason, they split apart and drifted away. And the pieces slowly moved to their current locations. He was not the first person to notice that the continents look a little bit like puzzle pieces that might fit together, but he took it a little bit further. He looked specifically at the continental shelf of the continents, which fits together even better. He noted that there were geologic structures and specific fossil assemblages that matched up precisely on either side of the Atlantic. So he concluded they must have been together and somehow drifted apart. This theory was just mercilessly scorned during his lifetime, and he died in 1930. The problems were that the evidence was all observational, and he had not explained how and why the plates would move. The idea finally started to gain a few proponents in Europe in the 1950s when little bits of supporting evidence started trickling in. Paleomag for some of the people here. But the US scientists still just universally hated this theory, like emotionally hated it. They were very, very opposed. But their main beef was that nobody had proposed a mechanism for how these plates would move. Were they just plowing through ocean crust? Why would they move? Did not make a lot of sense to them. So this is the scientific climate as Marie gets started. These are some of the profiles that she made with the echo sounding data of the mid-Atlantic. And you can see, as she saw, that the mid-Atlantic ridge stands out pretty well there. And this is basically the first time that the ridge was clearly documented in any way. But she also noticed that there seemed to be a notch at the top of the ridge on all the profiles. She concluded that there was a continuous rift valley that ran along the ridge, and she thought that it could be evidence of continental drift. She's quoted as saying, if there were such a thing as continental drift, it seemed logical that something like a mid-ocean rift valley might be involved. But I think that she was a scientist, so she had the background knowledge to make this leap, but she was also a step removed from the actual scientific community, so I think it was easier for her to propose that or to espouse something that reeked of continental drift. Bruce, on the other hand, was not convinced that the rift was there at all. He didn't believe that it was continuous. And Marie thought that he was specifically resistant because it could be supportive of continental drift. He's quoted as saying, in 3 of the transatlantic profiles, the top 3 there, she noticed an unmistakable notch in the mid-Atlantic ridge, and she decided there was a continuous rift valley and told me. I discounted it as girl talk, didn't believe it for a year. This is sort of a famous quote of his. And he was not convinced at all until work on an entirely separate project corroborated it. So Bruce had earlier discovered that underwater landslides could break telegraph cables. And those landslides can be caused on slopes by earthquakes. This 1929 earthquake, you can see the epicenter is the star there in the middle. And by looking at the timing of the quake and the timing of the break of each of the cables, he showed that the breaks radiated downslope, and he calculated that this landslide could be going at about 30 miles per hour and reach for 200 miles. So not awesome conditions for laying cables. And Bell Labs hired him to help them figure out where the safest spots would be to avoid these landslides. So for this work, he had a young man named Howard Foster plot out all of the epicenters of tens of thousands of earthquakes in the Atlantic. And Howard was basically an intern. He was the son of the cook and chauffeur of a wealthy Woods Hole oceanographer who offered to pay Howard's salary, and so Bruce put him to work. But meanwhile, Marie was working in the same room on her maps, and they were fortuitously at the same scale. And when both maps were put on a light table, they made a huge discovery. The epicenters lined up with the Rift Valley. So if Marie was right about the rift, then the earthquakes could be related to the crust pulling apart, lending strong evidence to that idea. And it also meant for the maps that she would know exactly where to put the rift in between the profiles because she could just track the epicenters. Now, it's not clear who suggested putting the maps together on the light table, and it's not clear who noticed the correlation. But for a long time, the official story was that Bruce and Doc Ewing had made the discovery. But the earliest record of Marie telling the story, she says she noticed the correlation and told Bruce. Bruce later contradicted her in an interview. And every other time that she talked about this publicly was after Bruce had died, and she tended to give him credit for everything at that point. But I tend to believe she was the one behind the discovery. So this discovery also meant that they could take this information to other ocean basins, and they started to see that you could indeed make profiles and match them up with epicenters in other parts of the world. Soon they could see this rift was splitting seafloors everywhere. So Bruce took the idea of this global rift to Princeton to give a lecture in 1957. At the time, his preferred explanation was not a new idea, this old idea that the Earth was expanding and the continents were basically coming apart at the seams. It was one of the earliest explanations for why the continents look like puzzle pieces. And I think it's a fun idea. We could use more Earth. But one of the scientists who was there at that lecture was Harry Hess. He is a big, important name in the development of the theory of plate tectonics, which I'll get to in a minute. But after the talk, he reportedly said to Bruce, "You have shaken the foundations of geology." And indeed, news of the rift went beyond the scientific world. And you can see, if you can read the highlighted area, that Marie did get credit in this news story for making the connection between the rift and the epicenters. But for the most part, she doesn't get credit in the scientific community or in the public. And she's not an author on any of the resulting scientific papers, which were mostly credited to Doc and Bruce. And Doc, as the senior scientist, was the one to present this to the world, and that's him over there. In 1959, Bruce presented the global rift at a huge event, a landmark event in the history of plate tectonics, the International Oceanographic Conference at the United Nations in 1959. So there were 800 scientists there, all the big names in earth science. And this is seen as a turning point in the acceptance of the idea of continental drift and eventually the theory of plate tectonics. The maps and the rift were a big part of that shift, but at the conference, the map was not an immediate hit. The US scientists were still skeptical that the rift was continuous at all. They thought that a lot of liberty had been taken with the interpretation between the profiles. And the lore is that it was Jacques Cousteau who vindicated Marie's rift at this conference. When he had first heard about this and saw the maps, he also did not believe the rift was there and decided to disprove it by making an underwater film using this photo sled that he had just invented called the Troika. So he purposely went to an area in between the profiles to photograph the area and show that there was no rift. So he showed the footage at the conference, sort of an unscheduled evening event, and the film shows the approach. It shows the Troika climbing up the side, and when it comes to the crest, the huge dark valley appears. And then eventually, the other side of the rift materializes and the camera goes down the other side. Reportedly, the audience asked him to rewind it and show it several times. That did make an impression. The following year, in 1960, Harry Hess of Princeton, who I mentioned before, published his paper suggesting that the rift is caused by upwelling in the Earth's molten mantle. He called this seafloor spreading, and we finally have a possible mechanism to drive plate motion. I promise I'm almost done with the plate tectonics. So the other part of the mechanism is convection currents in the mantle that help push the plates around. This is the Pacific, where the ocean plates are actually being forced beneath the continental crust. In the Atlantic, the continents are connected to the ocean crust and the basin is widening. It is still widening at a rate of 1.5 inches a year, which might not seem like a lot, but it adds up in geologic time. After a million years, that would be 24 miles. So Marie and Bruce continued mapping and publishing more maps. This one's from 1961 of the South Atlantic. So using the physiographic method gave scientists a way to visualize something that looked familiar to them. They can all understand what a rift looks like and what that might mean. It's the comparison between continental landforms and the ocean that was helpful. This helped convince them that just as the East African Rift was splitting that continent, the submarine Rift Valley marked where the seafloor was pulling apart from itself. Here, again, is I don't know if I can make that go away. Anyway, the unfortunate, it's fine. Again, the rift peeking out through the neat line. And at this point, they're basically using this physiographic method to make an argument for how the features were formed. This became their most iconic scientific map, another posed photo of them. National Geographic took a lot of funny posed photos of them along the way. I don't know if that one's National Geographic, though. The Rift Valley is more easily seen on the South Atlantic map, and I think that this is partly because this map was a few years later and Marie was gaining confidence in their interpretation of what was going on there. And you can see that also on this update, 1968 update of the North Atlantic. The ridge is much more visible than it was. You can see that here. So here's what we understood before Marie's maps, data from 1912, and here's what we knew afterwards. So they made a huge impact on the scientific community's view of the ocean floor. Next, they would have an impact on the public's view of the ocean floor. And for that, we need to introduce another character in the story of these ocean maps. Anybody know who this is? So this is a man named Heinrich Baron. He's an Austrian artist who pioneered what is usually called the cartographic panorama. I'm also a huge fan of Baron. There's a story about him in the book as well. I just love that this map brings so many of my favorites together. So Baron's work caught the eye of National Geographic. This is one of the first things that he did for them. And in some ways, his panoramas are better than a photograph. He uses a little bit of, we'll say, creative distortion to move things around just enough. So for example, here you would be able to see all of the route up Everest, the two routes that are being described in the story that it went with. This is from 1966. This is a really, really nice fold out in National Geographic from 1985. Some of his best known work was for the National Park Service toward the end of his career. This is one of my favorites. This is an unusual view of Yellowstone looking from the north south to the Tetons in the distance. And this is a good map to use to show some of that distortion. So in the front of the center of the map, you can see the Grand Canyon of the Yellowstone. That is just much bigger than it actually is relative to the rest of the landscape. But because he did that, you can see the character of that canyon and understand much better what that's about. It probably would be very difficult to see otherwise. You can see Old Faithful is really big up in the top right over there. And the Old Faithful Lodge, which is behind it, as he's drawn it, would be 3/4 of a mile long, which is a little bit longer than it actually is. But the biggest change that he made is with the Tetons. He actually rotated them about 55 degrees. If you were looking at this for real, it would just be end on to the Tetons and you wouldn't really even be able to recognize them. So you could call that a liberty, but I think it makes sense in this case, and I really love that image. So in 1967, Nat Geo paired Baran with Bruce and Marie to do a map of the Indian Ocean. That is not very high res, is it? Sorry about that. Here she is again, pretending to work on a map, the physiographic diagram of the Indian Ocean. And here's what that looked like, published in 1967, their first collaboration. It's also in the display for Laura's talk over there. 1968, I think this one is gorgeous. That's on display over here. This is also on display in my office at home. The Pacific from 1969 and the Arctic from 1971. So their collaboration culminated in this amazing world ocean floor map. They did it independently. It was funded by the US Navy, imagine that. I don't think they'd fund anything like that at this point. And it took them 4 years to do this. I would call it an iconic cartographic masterpiece. I don't know about you. I think it's pretty cool. And this map is actually, if you go to earth sciences departments around the world, you've got a fairly good shot of seeing this on the wall somewhere. It still really characterizes the ocean floor in the minds of, I think, both scientists and non-scientists alike. And the original painting is over 6.5 feet wide, no, 6.2 feet wide. It's in the collection of the Library of Congress. They really don't like to bring it out. I still haven't seen it in person. Has anybody? No? I'm very stingy with that one. So here's a little bit closer, so you can see some of the details. And I think, yes, a little bit closer. So I just think about the size of this map and the number of seamounts in this little section and how much work this was for Heinrich Baran. It's kind of crazy. But he spared no seamount. They're everywhere. Here is Hawaii. But look at all of the time, like even the relatively flat place, it's just crazy. Here is, so you can sort of see the underlying scientific physiographic diagram that he was basing his work on. And you can also see he's put a little bit of red in the middle of the rift to represent the magma coming up, which I like. So Marie and Bruce traveled several times to Baran's studio in Austria to work on the map with him, and this is a picture of them there with the manuscript. Sadly, Bruce died of a heart attack just weeks before it was finished, and a couple months before it was published. He had a heart attack while on a submarine exploring the mid-Atlantic ridge near Iceland, which I suppose is appropriate. He was just 53 years old. When this happened, Marie was actually on a research vessel. She did manage to start getting to go on voyages about 20 years into her career. This is a picture of her there. And so there are questions about their relationship. Neither one of them was ever married. They didn't have kids. They were certainly a close collaborative pair. And Bruce did leave his house to her when he died. And I imagine that this was a pretty difficult moment for Marie. The map was really her crowning achievement. Earlier, Bruce had a huge falling out with Doc Ewing, and they were estranged, and so Marie was basically estranged from Doc as well. So when Bruce died, she had no source of funding, and her career was basically ended. It wasn't until 1997 that she was recognized by the Library of Congress, who included her work in a 100th anniversary celebration of the Geography and Map Division and named her one of the 4 greatest cartographers of the 20th century, which is pretty cool because she was still around to see this. That often doesn't happen, so that makes me happy. In 2001, Columbia gave her their Heritage Award and also named a fellowship after her that's given to female scientists to be visitors at Columbia. And she died in 2006, but her impact lives on. And though hers was always the second name after Hazen's, on the papers that they made and doesn't appear at all on many of the papers about her work. She never expressed any regrets about it or about her path. She's quoted as saying, "I thought I was lucky to have a job that was so interesting. Establishing the Rift Valley and the mid-ocean ridge that went all the way around the world for 40,000 miles, that was something important. You can't find anything bigger than that, at least on this planet." In 2009, Google added the map as a view in Google Earth. In 2013, a writer named Hallie Felt wrote a biography of Marie. And so you probably already know this, but I believe that the map remains the best view we have of the ocean and captures its essence better than anything else. So the GEBCO process goes on. This map is from 1961, 1978, and this is their most recent version from 2022. That's the full chart. So today, only about a quarter of the ocean floor has been mapped at a high resolution. In the vast rest of the expanse, you can easily hide an airplane within the resolution, as we have found out. So Marie recognized how unlikely her career was. In a 1999 perspective, she said, "It was a once in a lifetime, a once in the history of the world opportunity for anyone, but especially for a woman in the 1940s. The nature of the times, the state of the science, and events large and small, logical and illogical, combined to make it all happen." And Bruce also recognized what her legacy was. In 1975, he said, "What people think the bottom of the ocean looks like, what most scientists and what most informed laymen think it looks like, is what Marie thinks it looks like." And because we cannot see it with our own eyes, and because most of it has yet to be physically explored and mapped in any detail, I would argue that 50 years later, this is still true. Our conception of the ocean is Marie's vision of it. That's it. Look at that, 42 minutes.
We're going to start Q&A here in a second. I have a mic I'm going to run around the space with. So just raise your hand. We're going to start with questions from the room. And if we have time, we're going to answer questions from Zoom.
Do you know how they picked the projection for the global map? Because Mercator is maybe not the greatest choice.
No, it's maybe. My guess is that was Baran's choice, but I haven't found anything about that anywhere. And it was, it was the choice that everybody was making at the time, more or less. Laura, that's it.
Oh, sorry. I will actually use the microphone. I feel embarrassed that I didn't recognize that picture of Heinrich Baran. I've actually never seen his picture before. So
there are not very many pictures.
Yeah, that was wonderful. My question was about Jacques Cousteau's film. Have you seen that film? Because I am so curious about seeing this film of the Mid-Atlantic Ridge. Do you know if it's anywhere, and has anyone, recorded it for posterity somewhere?
I like to think it exists somewhere. I have not found it yet. I've looked through, scanned through, and again, before this talk, I was like, maybe I'll try again. I may just be missing it in some of the many several hour-long films that he's got, or maybe it's just not on YouTube. I don't know, but I haven't found it yet. I'm really curious too. If you find it, please let me know.
Hi. Was curious about the 1959 or 57, UN conference.
Yeah,
You
59,
mentioned.
yeah.
I mean, did that effectively become like the definitive, validation of the drift? I mean, or how long did it take, that to actually sort of, sit and become historically valid?
I'm not going to be able to give you a specific answer, but I do think that, yes, that was the turning point, that European scientists had mostly accepted this idea, and it was the US scientists who were still resisting it. And their main issues with it were kind of being swept away. We now know that, yes, it is continuous in between. There's lots of data showing that, with the epicenters and Jacques Cousteau showing physically that it's actually true. And then also, if it's true, then we start to have a mechanism for why the plate might be coming apart there, and why plates would be moving around at all. So historically, it's cast as a turning point. I don't actually know how long it, were they still grumbling as they left the UN building, maybe? Or were they like all happily joining hands? So far my answers are, I don't know, and I don't know. Ask me something I know.
Well, you might not know this, although you might. When she died, Marie's daughter contacted me as a collector and asked, what should she do with Marie's papers? And I said, Library of Congress, but I never heard back from her.
So I think that, I don't think that was her daughter. I think it was a woman, I think her name is Sophia, maybe?
Oh, you're
something like
right.
that, who is basically her assistant, caretaker.
Of course, she didn't have a daughter, of course.
Yeah,
Yes.
and so, and Marie, and this woman is, I can't believe she contacted you. Like, she's extremely difficult to reach. Every time I try to reach her, it takes me months to get her to respond to an email, because Marie left her the copyright to all the maps.
Yes, yes.
And so, occasionally I have to contact her and ask her for permission to use the
I've
maps.
done the same thing.
Yeah, which is difficult.
Yeah.
But if she's been in contact with you, then, maybe we should talk about trying to help her make these maps more available.
Yeah, that's a great idea. Up for that.
Okay, great.
Thank you. I was wondering if you know how much of this ocean bathymetry was actually interpolated on this map, and also, if it is, do you know how it was interpolated?
Yeah, I mean, the data points, relatively speaking, there's not that much data. So, I mean, the big advance was knowing where to put the rift, and they did have some, which they learned based on the epicenters, where to put the rift in between the profiles, where it wasn't actually measured. And so, a lot of this is an educated guess at the time. I think probably Jacques Cousteau's film was helpful, and they did have some photographs from the research vessel Vima scattered around, but they were mostly pretty close-up pictures. They weren't sort of landscape shots that would help you with the terrain. So yeah, there's a lot of imagination involved here. But I think it's a reasonable assumption that the landscape in between the parts that they knew better was probably similar to the parts that they had more data on. Especially once you buy the explanation that it is a giant continuous rift valley.
Well, almost the same question. Maybe you'll answer a bit differently.
Maybe.
But I was wondering about exactly this. I wouldn't have formulated this interpolation, but that's exactly right. You have like biased data, which might be constructed by shipping lanes. So would that be the kind of thing that would really give you very bad profiles, profiles that have nothing to do with the geological process, but have to do with how ships go on the surface?
Yeah, I think that would probably be true, except that the data that they used was primarily from those two research vessels. And one of the things that those vessels were trying to do is map the ocean floor. they were doing a bunch of other oceanography research, but they were attempting to get some kind of reasonable coverage for that purpose. It's still pretty sparse, and prior to that, I think there was quite a bit of just luck as to where the data was on those earlier maps that I showed. But it was in 1870s that they started purposely trying to map the ocean floor because there was economic interest to do so because of the telegraph cables.
You almost answered my question at the very end. These are wonderful maps, groundbreaking, but you mentioned these are late 60s, early 1970s. With all the technology that we have now, has there been a map that gives a much better representation of the ocean floor?
And Laura might be a better one to answer that, but the best data that we have is all collected. The best public data that we have that this group is able to get a hold of, we have here. But the 75% of the ocean floor that has not been mapped in detail by underwater vessels is basically satellite data. So if there's a big enough structure under the ocean, it will have enough gravitational pull to mound some water over it, and you can measure that with the satellite and interpret what might be below. So a lot of that, I think, if Laura agrees, is what this map actually is, except for the areas where we have had subsea vessels going down and doing closer looks.
Thank you.
So that's part of my argument is that we don't have the data to visualize it in more detail than Marie's map does.
Thank you, Betsy. That was a great talk, and it was particularly touching to me because I was at Lamont, and I went to Lamont as a postdoc early because Bruce Hazen died of a heart attack on a submarine, and we picked up his projects from then on. So I never knew him, but I did get to know Marie just very briefly.
Oh, really? Oh,
yeah,
that's so
but,
cool. I didn't know that.
Yeah, so it's kind of like the beginning of my career, but I think the satellite data that they have now is pretty good for understanding the physiography of the ocean floor. But what you said is right. We don't really know what the detail is down there, like on a granular detail. We know more about the surface of Mars than we do about the ocean on Earth, except for the places that people have gone down with submarine bathymetry studies and done these really detailed scans. And people have gone and studied mid-ocean ridge processes. So like in places, there are postage stamps that are super well mapped. Mm-hmm. Yeah, but it's not the entire ocean. And there's people in our field that dream that someday we'll know the surface of the Earth and the oceans as well as we do Mars.
Well, we, as a species, might. You and I might not.
Yeah, I was just going to add to what Betsy said, to an earlier question that was asked. I think that you're right, that I think that these are the best maps that we still have, just because they create like a full overview of the ocean. And you can find really good, better maps today, for sure, that are maybe based in better, more rigorous scientific data. But I feel like you're right that Marie Tharp created that overarching view that we still don't have. So yeah, I just wanted to follow up to that question that was asked earlier.
Thank you. Yeah, I think, I mean, for me, it's really that, the map captures the essence of the ocean floor, the character of it.
I'd also say that nobody has 4 years to devote to a single map anymore.
Yeah, another part of my argument as for that part of the reason this is the best map we'll ever have of the ocean is that nothing like this is ever going to happen again, where you would have the Navy funding years of work with an artist and scientists putting this kind of effort and detail into a map. It's just, that's not how we do it anymore.
So I'm going to go back to a tectonics question. How did they know about and interpret the transverse ridges?
So how they first found them, I believe, was probably from some of the transects that they had. But you can see in the evolution of her maps those showing up more and more. So as they had better data, they got that. So he's talking about the lines that you can see going across perpendicular to the ridge everywhere. Those are basically strike slip faults. So the crust is not pulling apart at exactly the same rate. They're moving at different times. So you've got little sections that move together, and then there's faults in between transecting it. I don't know exactly what the first data was for that, but you can see it in the difference between the map that we have on the wall there from 1959 and the second version of that I showed that has all those transects on it is a huge difference.
Yeah, a seminal contribution to that was Tuza Wilson's identification of the transform faults, which came out of a different study, but all of a sudden people realized that they could connect segments of the ridges with the transform faults, and I think that was a major contribution at that time.
Thank you. It's always nice to have geology professors in the room.
Do you know if she had benefited in the geomagnetic surveys across the ocean?
I don't think that she did. I mean, that's some of the data that started to convince the European scientists. But, as you probably know, there was then, so the geomagnetic data is looking at which direction the rocks, where the pole was when the rock was formed. You end up with some magnetic minerals lining up, pointing at the pole. And so you can back calculate some things about where that would have been when the rock cooled and the minerals formed. But there was some question as to whether the pole was wandering, and that could explain why those things were changing instead of plate motion. And I don't know exactly when that was happening. You probably know better than me, but I think that was like late 1950s that started to come in. And, they were making the map right then. I don't think that I didn't read anything in all the many things that I've read about her that, or about that work that suggests that. Though I did read most of it 10 years ago, so it's possible that I just don't remember. Yeah, the painting.
Yeah, I had a question on the choice of colors. So the ridge is kind of a dark purple, and there, I think, are other below sea level mountains and features that are various shades of blue. And why the ridge is not just the ridge itself is purple, but I don't know, away from it is also purple, slanting downwards. So anyways, just kind of a question on colors, because it's not the same elevation guessing that the shades of blue are. Does that make sense?
Yeah. I do not know, but I'm guessing it was mostly an aesthetic choice for the ridge to stand out the way that it does. But you're right, there is some of your typical shading for depth in other parts of the ocean. So the ridge was really the focal point of the map. And so I think they just wanted it to stand out, but there's other options. That's how they did it for National Geographic, a little bit different. And the colors on this map are a little bit exaggerated on this screen. It's not quite that bright in real life. It's closer to it's closer to the one on the wall that you can see there. I don't know, I think it looks nice. I like the choice.
I have good news. There's catering downstairs for our reception. We are just at time. I know there were a couple of questions that were left on Zoom. There might still be some questions left in the room. Maybe we can use the time in the reception to speak with Betsy. And anybody who's on Zoom that has a pressing question that they would like an answer to, you can follow up with the David Rumsey Map Center, and we'd be happy to relay those questions. So I am here to tell you, we are ready to get up. You can gather your things, walk downstairs, or take the elevator. There's food and refreshments directly below us on the second floor, and we'll be there for about an hour. Don't leave anything in this space. We're going to lock the door. The alarm will go off if you try to get back up. So please take your things with you, and we'll reconvene downstairs.
Thanks for coming.